So I'm going to start with this photo. Hopefully you can see it. It sort of encapsulates a lot of what I work on. So I think about the impacts of environmental change on social and economic systems and how humans interact with their environment. If you can see in the image here, there's a burning wildfire in the background. This is a shot from Oregon a few years ago. A couple folks watching, potentially concerned about the wildfire. These guys in the front just playing golf. So it's a photo as metaphor for our relationship to the environment. But I don't want to start you there. I want to start you somewhere else. So this, I think, is the lowest income or least economically developed place I've ever been to in the world. This is in southwestern Niger. You can see the Niger River in the foreground here. This is a village that for most of the year is actually not accessible by road. We had actually paid some guys to take us down the river in the boat. Yeah, this is a poor part of the world. You might know or anticipate some things about this part of the world. What do we know? Well, number one, we know it's hot. This is in the Sahel. Hard to see on the map here, but if you know where the Sahel is, Niger, about 30 degrees Celsius average temperature, 85 Fahrenheit, annual average temperature, so very hot. It might be hard to see in this image, but it's also suffers for much of the year very bad air quality due to dust that blows in from the Sahara. So here are remote sensing estimates of PM 2.5, small particles that we know are important for health. And when we normally think about dirty air around the world, we tend to think of the Asian context, South Asia, East Asia, but it turns out parts of West Africa have air quality that are just as bad as the dirtiest parts of Asia. So micrograms per cubic meter of PM 2.5 up above 100 annually and seasonally much higher than that. And so what my research tries to ask is there actually a relationship between development outcomes broadly understood here and the environments that people find themselves in, the environments they're born into or live in. So let's look at some data. Average temperature and PM 2.5 I told you before. Income per capita here, I took a guess. We actually don't have survey data from this village, but I'm going to say it's $250 annually, so less than $1 a day per household. This is, again, extremely low income, poor villages. And infant mortality, my best guess from the data is about 15%, right? So more than 1 in 10 kids don't make it to their first birthday in these villages. Okay, let's compare it to then another place we know well. This is our campus. What are some data from Palo Alto? Average annual temperature about 13 to 14 degrees Celsius. 50 to 60 degrees Fahrenheit, right? Temperatures we're used to. Our air quality is, for the most of the year, pretty good. We'll come back to that. 8 micrograms per cubic meter, much lower. And coincidence or not, we are much wealthier, right? So average per capita incomes, recent census data suggest about $80,000. In many zip codes, as we know, it's much higher. And infant mortality is quite low. 0.2% was the closest estimate I could find for Palo Alto. So it's cooler here, better air quality, and much better economic outcomes. Are these two things just randomly correlated, or are they potentially causal? And that is what my research tries to understand. So what are the challenges when you try to quantify these environment-society linkages, when you try to understand potential causal relationships between air quality and temperature and health or economic outcomes? Two main challenges. Number one is measurement. And I'll come back to this, but often we do not measure either the environmental exposures or the economic or social outcomes in a way that lets us get anywhere near this question, right? We're just not collecting the data that we need to answer this question. For Palo Alto, I could get pretty good data. I could go into census and look these up. For southern Niger, basically a data-free environment. Surveys aren't done. We don't have sensors. We aren't making the measurements. So that's number one. Number two, even if you have the measurements, is an inference challenge, right? We want to make causal statements about the relationship between environmental variables and economic outcomes. How do we do that? We can't run randomized control trials, typically in these environments. We can't randomly assign temperature to people. It's impractical. It's often unethical. And so we have to work with the data that we're given, right? And we have to exploit the variation in that data that nature or policy gives us. So we have to be clever about the inference question. Okay, so let's go back to this, and I want to zoom in on a couple inference questions that we and others have worked on here. So let me highlight here the poor air quality and the high infant mortality. And we want to understand, are these two things causally related? Does higher levels of air pollution, in particular PM2.5, which is what I'll focus on, does that lead to, and can we attribute lots of the infant mortality to higher levels of pollution? Okay, what's the measurement problem? Again, we don't have any sensors. On the continent of Africa, there is now fewer than 5, and when we did this study, there were 0 publicly available PM2.5 sensors that reported to international agencies. Literally on the entire continent, no PM2.5 sensors, right? So no pollution information. Most of these countries also do not collect vital statistics data, right? So we are well aware of mortality rates in much of the world, and that is due to a system of vital statistics we have that collects data on who's living and when people die. Most countries in sub-Saharan Africa do not have vital statistics data, and so we just can't go on a website and look up mortality rates. Similarly, on the inference side, so let's say we could actually observe these things, how do we actually understand whether pollution is a cause of these outcomes, right? Pollution levels could be correlated with all sorts of other things that could also affect infant mortality. So the trick is to isolate the component of pollution variation that's not correlated with that other stuff. So how do we do that? Okay, here's how we do it. On the measurement side, we are going to exploit a wonderful set of surveys that were funded in large part by the US government and carried out by the demographic and health surveys around the world. These are surveys, individual household surveys, where surveyors go out and survey households. The sample frame is moms of childbearing age. You can see the mom here. And among other things, they ask them about their entire birth history. So they elicit when moms had kids, when those kids were born, and whether or not the kids survived. What they also do, and critically for us, is they geo-reference the surveys. So we don't know exactly where the household is to protect privacy, but we know where the village is. And so these different dots show the roughly 1 million births that we can observe in these data over the last 15 years. So a really, really rich data set on where kids were born, when they were born, and whether or not they survived to their first birthday. Okay, that's on the outcome side. How about the exposure side? So again, I told you there we did not have pollution monitors. Instead, we're going to use remote sensing. This is not our own product. We're going to use someone else's product that used a variety of remote sensing products and techniques to try to estimate year-to-year or month-to-month variation in PM2.5 around sub-Saharan Africa. These models turn out to be very hard to validate, again, because we don't have the ground data. It's something we're working on right now, but this is sort of our best guess of what the pollution was in any location in any given time period around sub-Saharan Africa. Okay, so how do we relate these two things? Again, I showed you a picture of Niger, and I showed you a picture of Palo Alto. They have different infant mortality rates, and they have different pollution levels, right? Do we want to attribute those differences to the different pollution levels? We probably don't. Niger, Dosso, Niger, and Palo Alto, California are different in all sorts of ways that are correlated with the pollution levels, right? So we don't want to just attribute that difference to pollution. Instead, what we're going to do is we are going to just focus on a given location and look at variation over time as PM2.5 fluctuates. In some years, the winds really pick up and bring a lot of dust from the Sahara into these villages. In other years, they don't. And that gives us plausibly random variation in year-to-year variation in PM2.5. And we can use that variation then to trace out the effect of increasing PM2.5 on infant mortality. And that's what you see here. So we can look at how kids do after they're born as a function of exposure during that time. We can also look at if kids are exposed in utero to pollution, how does that affect their later life outcomes or their mortality rates? And we see strong upward sloping relationships between increasing exposure to PM and both when you're in utero and post-birth on infant mortality. Okay, happy to go into more of the details if folks are interested, but once you trust this model, and we beat it up a lot, we can actually use it to do attribution. We can use it to understand, okay, what proportion of the observed infant deaths that we see are attributable to this air pollution. And here's a map showing our estimates of that for the countries where we had data. Niger, we actually didn't have data, but we had data close by in Benin. And there we find roughly a quarter and up to 50% of the infant deaths in these regions are attributable to just this one factor, to variation in PM2.5, right? So a very, very strong coupling between environment and a key health outcome in this setting. Okay, let's look at one more. Here is the relationship between hot temperatures and low incomes that I showed you before. Is there plausibly a causal relationship here? Okay, a naive analysis might do the following. I could take data from countries around the world, I could compute their GDP per capita, and I could relate it to their average temperature. And then I could fit a heroic regression or a fit between these data. So that's what's shown here. If you sort of blur your eyes, this thing is downward sloping. A lot of variation around that line. So you might be concerned about the variation, number one, but you should be even more concerned about the causal inference here, right? Because again, we don't want to compare Niger to Norway. They're different in all sorts of other ways that could be correlated with their average temperature. So we got to, again, figure out how to solve that inference problem. How are we going to do that? We're going to follow the same playbook. Instead of comparing Niger to Norway, we're going to compare Niger to itself over time as the temperature plausibly randomly fluctuates. We're going to do the same thing in Norway, and then we're going to combine the estimates. Here's what we get when we do that. So this is using 70 years of global data, GDP data from around the world. So back to about 1950 when we started collecting these data in earnest, we, the system of national accounts. And what do we see? So this is the relationship between annual average temperature on the x-axis, and on the y-axis, it's the growth rate of GDP, the sort of headline number that we're used to thinking about. In really cold areas, what we find is that if you're in Greenland or Iceland and it warms up, you're actually more productive. And I think this is intuitive, right? In a really cold place, think about the Antarctic, right? As it gets warmer, there are more things you can do economically than you could do when it was much colder. So in cold places, the effect of warming is actually positive. In most of the world, you're warm enough that we find the opposite effect. Very clear evidence that warming temperatures reduce economic output and reduce how quickly economies grow. Okay, where does this thing peak? It peaks, it turns out, at about 13 to 14 degrees Celsius. You want to recall the annual average temperature of Palo Alto, California. So it just so happens that the comfortable climate that we live in is, by this estimate, the global optimum temperature for economic productivity. What's the annual average temperature of the US as a whole? About 13 degrees Celsius. New York City, 13 degrees Celsius. So many of the wealthiest parts of the world, coincidence or not, turn out to be quite wealthy. Okay, we can take that historical relationship and using climate data, and this is work with Noah Diffenbaugh, see the citations, we can heroically run the world forward and estimate what would happen under different warming scenarios. This is an older plot from RCP 8.5, which is now deprecated. We hope the world is not going to warm 4.5 degrees now, so these are higher numbers than what we would estimate now. These numbers estimate how wealthy you would be relative to a world that didn't warm. And what do you see? A few high-latitude countries seem to benefit. Most of the world seems to be harmed. In Niger, we see 50 to 60% lower incomes than you would have had warming not existed. So huge negative impacts on productivity. Okay, let's come back to California quickly. I want to do wildfires in the last minute. We have pretty clean air most of the year. If anyone has lived here for the past few years, you know that we should no longer take that for granted. Here is our impressive progress on air quality around the country. This is a huge public policy success. This is contiguous US, and it's a little hard to see the lines. Regional trends in PM 2.5. These have been going down. These have been going down almost entirely due to the Clean Air Act and its subsequent amendments over the years. Huge policy success. Okay, look at the last 5 years. These gains have either flattened or reversed throughout much of the country. In the West, they've reversed pretty dramatically. Our question is this wildfires? We know there's been a large increase in wildfire activity in area burned in the West or in California. You don't even have to see my crappy regression fit to believe that these are upward sloping. Large increase in wildfire activity, are these to blame for the PM 2.5? So work led by Marissa Childs in my group tried to understand this. So we built a machine learning model to predict variation in wildfire smoke across the entire US using a range of remote sensing and ground measured inputs. Happy to go into more of the details. The model worked really well. It explained 70% of the day-to-day variation in smoke exposure. Once you have a model, you can make animations like this that show for 2020 the wildfire smoke-derived PM across the entire US. You'll see this start to pick up. So summertime, see more and more fires in the West. And in August, we'll get the big fires starting here. If you remember the apocalyptic days of orange skies, that was August, September. These last for multiple months, and then fires sort of die out. So remarkable temporal and spatial variation in wildfire exposure. And what we can do is then go back and estimate, and we got one of those plots right into the New York Times, which I was proud about. We can go back and estimate what would have air quality looked like absent these wildfires, or how much of the reversal is due to wildfires. And we find that in some regions, and especially in the West, most of it is due to wildfires. So the blue lines would be what would have happened had we taken wildfires out if we had had no wildfire smoke, and the black line is what we actually observed. So a lot of the recent increases are attributable to wildfire smoke. So let me finish up. The hope is to use this sort of information to inform policy in various ways, so understand where to intervene environmentally with environmental policy, the benefits of that intervention, or alternatively, the cost of inaction, what we're going to face if we don't get our act together. Thanks.